This lecture introduces the concept of a layered protocol architecture and the function of the TCPIP protocol suite. TCPIP is an internet-based protocol suite and is the framework for developing a complete range of computer communication standards. It specifies how data is exchanged over the internet by providing end-to-end communications that identify how it should be broken into packets, addressed, transmitted, routed, and received at the destination. Let us first look at an example of file transfer between two computers to understand why we need a protocol architecture. At first, this may sound like an easy task, because we do this all the time. However, in reality, it is very complex. First, there needs to be a data path between these two computers before a file transfer can happen. The source computer must either activate the direct communications path or tell the network what is the destination computer. The source computer must make sure that the destination computer is ready to accept the file. The file transfer application on the source computer must make sure that the file management program on the destination computer is ready to accept and store the file. Finally, if the file formats on the two computers are different, the format of the file needs to be translated so that the computer can read it. As you can see, there are several steps that occur that make this process of a file transfer more complex than it seems. That is the reason why we need a protocol architecture, so that all of these tasks are implemented as separate subtasks rather than one large task. With any complex problem, the easiest way to go about solving it is to break it up into smaller and simpler problems. That is the function of the protocol architecture. Imagine in our previous example of the file transfer if this was treated as one large task. If one part fails, for example, the format translation step, then the entire file transfer fails if this was one large task. However, if we break it up into separate steps, as in the protocol architecture, only that format translation step would fail, but the file would still transfer. So the entire process does not break. That is the reason and function of a protocol architecture. Each step in the process is broken up into separate modules and implemented as a vertical stack, where each layer of the stack has its own functions and relies on the next layer. If there are any changes or errors that occur on one layer, this does not affect the other layers. It is modular in design. It takes two to communicate, so the same set of layered functions must exist in two systems. The only way communication can work is if the peer layers communicate with each other. When peer layers communicate, they must follow a set of rules called a protocol. The protocol defines the syntax, which describes how the data should be formatted, the semantics, which controls error handling, and the timing, which includes speed matching and sequencing. Data communications usually involve applications, computers, and networks. Applications can include file transfer, email, and others. The applications are executed on computers in which multiple applications can be run at the same time. Computers are connected to networks, and the data to be exchanged are transferred by the network from one computer to another. Thus, the transfer of data from one application to another involves first getting the data to the computer where the application resides, and then getting it to the intended application within the computer. Because data communications involve applications, computers, and networks, it makes sense to organize communications into three independent layers: the network access layer, transport layer, and application layer. The network access layer deals with the exchange of data between a computer and the network. For this to work, the address of the destination computer must be known so that the data can be routed to the destination computer. The transport layer is responsible for end-to-end communication over a network, and it makes sure that data can be exchanged reliably. So it ensures that the data arrives at the destination and in the order that it was sent. This is independent of the application. The application layer provides services for an application program to ensure that effective communication with another application program on a network is possible. This figure illustrates the simple architecture that we have described of the network access, transport, and application layers for each of the three computers. So we have computer A, computer B, and computer C. The computers are connected to a network in which they can all communicate to each other. In this three-layer model, two levels of addressing are needed. Each computer on the network must have a unique network address, which allows the network to deliver data to the proper computer. Each application on a computer has an address that is unique within that computer to allow the transport layer to support multiple applications at each computer. These application addresses are known as service access points, or SAPs, or ports, as we can see circled here. Thus, each application is individually accessing the services of the transport layer. Modules at the same level on different computers communicate with each other by means of a protocol. For example, an application like a file transfer application in one computer communicates with an application in another computer using an application level protocol like the file transfer protocol, or FTP. This exchange is not direct, as we can see by the dashed line in the figure. But it is facilitated by a transport protocol that handles many of the details of transferring data between two computers. The transport protocol is also not direct, since it has, as we can see, it also has a dashed line, but relies on a network level protocol to achieve network access and to route data through the network to the destination system. Let us trace a simple operation as an example. Suppose that an application associated with port 1 at computer A wishes to send a message to another application associated with port 2 on computer B. The sending application generates a block of data and passes this to the transport layer. If this block of data is long, it is broken up into smaller chunks. Each of these pieces appends a transport header containing protocol control information. This is known as encapsulation. The combination of data from the next higher layer and control information is known as a protocol data unit, or PDU. In this case, this is a transport PDU, also known as a segment. The header will contain information such as the source port, which is the application that sent the data, destination port, because it must know which application the data is to be delivered, sequence number, to put the pieces of data back together when it reaches the destination, and error detection code, also known as a checksum or frame check sequence. The transport layer next hands the segment over to the network layer, where a network access header, which is here, is now appended to the data from the transport layer, creating a network access PDU. Now, this is called a packet. The header of the packet includes the source computer address, destination computer address, so that the network knows which computer to deliver the packet, and facilities requests such as priority. The transport header is not visible at the network access layer. The network access layer is not concerned with the contents of the transport segment. The network accepts the network packet from A and delivers it to B. The network access module in B receives the packet, strips off the packet header, and transfers the enclosed transport segment to B's transport layer module. The transport layer examines the segment header and, based on the port field in the header, strips off the header and then delivers the enclosed record to the appropriate application. In this case, the file transfer module in host B, and transfer is complete. The TCP/IP protocol architecture was developed in the 1970s as part of the Research Network, which was a packet switch network developed by the United States Defense Advanced Research Projects Agency, or DARPA. This network was initially called ARPANET and was designed to use a number of protocols that had been adapted from existing technologies. That is why the TCP/IP protocol architecture is commonly known as the TCP/IP protocol suite. The TCP/IP stack is a complete set of networking protocols. From our example of transferring a file between two computers, as we discussed before, we can actually organize the entire communication task into 5 relatively independent layers: the application layer, the transport or host-to-host layer, the internet layer, the network access or data link layer, and the physical layer. Sometimes you will see the TCP/IP model as actually consisting of 4 layers, where the network access layer and physical layer are combined together into one layer. We will discuss what each of these layers do in the upcoming slides. Starting at the bottom of the TCP/IP stack is the physical layer. This layer consists of the physical interface between a device, like a computer, and a transmission medium, such as optical fiber, twisted pair, or satellite. This layer is focused on the transmission of the bit stream and specifies the transmission medium, signal encoding techniques, data rate, bandwidth, and physical connector. On the layer above the physical layer, we have the network access or data link layer. This layer provides a logical interface to network hardware and is concerned with access to and routing data across a network for 2 end systems attached to the same network. Example protocols at this layer include Ethernet, Wi-Fi, ATM, and frame relay. In situations where 2 devices are attached to different networks, the internet layer comes into play, where the Internet Protocol, or IP, is used to provide the routing across multiple networks. The internet layer also defines an official packet format. The internet layer's job is to allow hosts to inject packets into any network and have them travel independently to the destination. Basically, it delivers IP packets where they are supposed to go. Packet routing is the major issue here, as is avoiding congestion. Example protocols in this layer are IP version 4, IP version 6, Address Resolution Protocol, or ARP, which is used to discover the MAC address of a device associated with a given IP address, and Internet Control Message Protocol, or ICMP, which is an error reporting protocol when network problems prevent the delivery of IP packets. The next layer up is the transport or host-to-host layer. It is designed to allow peer entities on the source and destination hosts to carry on a conversation. 2 end-to-end transport protocols are defined here. The first one, TCP, or Transmission Control Protocol, is a reliable, connection-oriented protocol that fragments the incoming byte stream into discrete messages and passes each one on to the internet layer. At the destination, the receiving TCP process reassembles the received messages into the output stream. TCP also handles flow control to make sure a fast sender does not flood a slow receiver with more messages than it can handle. The second protocol in this layer, UDP or User Datagram Protocol, is an unreliable, connectionless protocol for applications that do not want TCP sequencing or flow control. It is also widely used for applications in which prompt delivery is more important than accurate delivery, such as transmitting speech or video. The topmost layer of the TCP/IP stack is the application layer. It contains all the higher level protocols needed to support various user applications. For each different type of application, a separate module is needed for that particular application. For example, the File Transfer Protocol, or FTP, provides a way to move data efficiently from one machine to another. SMTP is the protocol used for electronic mail. Telnet, which is a virtual terminal protocol, allows a user on one machine to log onto a distant machine and work there. The Domain Name System, or DNS, is used for mapping host names onto their network addresses, and Hypertext Transfer Protocol, or HTTP, is used for fetching pages on the World Wide Web. These are just a few examples of the different types of protocols on the application layer, but there are many others. Putting all of these concepts together, we see how communications happens between two host devices on different networks. Host A is on its own subnetwork, while host B is on a separate subnetwork. There is some sort of network access protocol, such as Ethernet or Wi-Fi logic, used to connect a computer to a subnetwork. This protocol enables the host to send data across the subnetwork to another host, or to a router that will forward the data, as in this case with host A and host B, since the target host is on another subnetwork. IP is implemented in all of the end systems and the routers. It acts as a relay to move a block of data from one host through one or more routers to another host. TCP is implemented only in the end systems. It keeps track of all the blocks of data to make sure that they are all delivered reliably to the appropriate application. Each host on a subnetwork must have a unique global internet address. This allows the data to be delivered to the proper host. Each process with a host must have an address, or port, that is unique within the host. This allows the host-to-host protocol, or TCP, to deliver data to the proper process. As one host sends a message to another host, control information as well as user data must be transmitted. If host A sends data to host B, this block of data is passed via TCP. We are looking at going down this diagram if we are sending data. If this data is large in size, it may be broken down into smaller pieces. TCP appends control information, known as the TCP header, to each of these pieces, forming a TCP segment. This header contains information such as destination port, so that it knows to whom the data is to be delivered, sequence number, so that the segment can be reordered at the destination if it arrived out of order, and checksum for error detection. TCP hands each segment over to IP with instructions to transmit it to host B. These segments must be transmitted across one or more subnetworks and relayed through one or more intermediate routers. IP also appends a header of control information to each segment to form an IP datagram. This header contains information such as the destination host address. Finally, each IP datagram is presented to the network access layer for transmission across the first subnetwork in its journey to the destination. The network access layer appends its own header, creating a packet or a frame. The packet is then transmitted across the subnetwork to a router. Now, when data is received at host B, the reverse process occurs. So now, instead of going down, we are going up the diagram. At each layer, the corresponding header is removed, and the remainder is passed on to the next higher layer. So this continues until the original user data is delivered to the destination process. For most applications, the transport layer protocol is TCP because it provides a reliable connection for the transfer of data between applications. A connection is simply a temporary logical association between two entities in different systems. A logical connection refers to a given pair of port values. For the duration of the connection, each entity keeps track of TCP segments coming and going to the other entity in order to regulate the flow of segments and to recover from lost or damaged segments, making TCP a reliable, connection-oriented protocol.